on the Fourier transform. Now, in the previous lecture, we had motivated the idea of the Fourier transform, or the idea of representing a function, a signal, in terms of sine waves. In fact, we said it's not really convenient to think in terms of sine waves directly. Rather, it makes more sense to think in terms of the underlying rotating complex numbers, which we call phasors. We looked at the function e raised to the power j omega t. And we looked at the effect that a linear shift invariant system with impulse response ht had on this. We saw that the output was of the form h at omega times e raised to the power j omega t, where h omega is integral h lambda, if you wish, e raised to the power minus j omega lambda d lambda. Now, several words of caution are in order at this point. One is that we are assuming here that this integral converges, which is not always the case. So, this input-output relation is meaningful only if this integral converges. If this integral does not converge, the physical interpretation is that when you feed an input of this kind, the output diverges. So, the output saturates at all points, right. So, in a linear shift invariant system where this integral does not converge for a particular omega, if you happen to apply that particular e raised to the power j omega t, the output would be for all t or would diverge for all t. That is what it really means. So, it is only when the output converges that this expression has a meaning. Now, we had also interpreted this whole discussion in so, we said that we could think of signals as vectors. In the limit, we said that every point in time could be thought of as an independent dimension to the signal. And in that case, what we are saying in this input-output relation is that when we give a vector of the form e raised to the power j omega t to the system, which could be thought of as an operator on the vector, the effect is to produce another vector which is collinear with this. By collinear we mean along the same direction. It is a multiple of the same vector, right. So, this is a very special kind of vector for the system, and that is the reason why, if we recall from our, we will also liken the idea of invariant system to the idea of subjecting a vector to the action of a matrix. For a discrete time system, we had explicitly written down the matrix that operates upon the sequence. If you think of the, see, for a discrete time sequence, it is so much easier to think of the sequence as a vector, because each discrete point or each discrete index of the sequence n can be thought of as a different dimension. If you have a finite number of non-zero samples, then it is a finite dimensional vector. On the other hand, if the sequence has an infinite number of non-zero values, then you have an infinite number of dimensions, but countable, right. In continuous time, the number of dimensions is uncountable. It is as many as the number of points on the real axis in the limit, yes. In any case, all these do have there is some commonality of interpretation. All of them can be thought of in the language of vectors, and that helps us a great deal in visualizing some of these actions from a perspective that is more easily understood. Now, this particular quantity h omega can also be given a very interesting vectorial interpretation. We shall look at that later. But at the moment, we should first complete our nomenclature in the language of vectors. We should complete the task of giving names. So, just as in the context of finite dimensional spaces, we have the notion of an eigenvector and an eigenvalue. Here, this function e raised to the power j omega t serves the role. It acts like an eigenfunction to the LSI system. It acts like an eigenfunction to the LSI system. And this, if the output of this eigenfunction converges, then h omega by which it is multiplied corresponding to that particular vector. So, there is an eigenfunction or eigenvector e raised to the power j omega t, and there is an eigenvalue h omega if it converges. If it diverges, of course, there is no point. I must here make a remark on the word eigen. The word eigen in German means own, one's own. So, in fact, this is the system's own function, in the sense that it remains undistorted after passing through the system. That is why it is called an eigenfunction, the system's own function. And the corresponding value or the multiplicative constant is called an eigenvalue. Now, the idea is this set of eigenfunctions is very powerful as a basis, just as the set of impulses formed a very useful basis for analyzing LSI systems. Similarly, it can be shown that in a wide class of situations, the set of functions e raised to the power j omega t for all omega constitute a class of, or a collection or a pool of functions in terms of which, as linear combinations of which we can express a wide class of functions that are input to an LSI. One can express a wide class of xt's that go into an LSI system as a linear combination of impulses appropriately shifted and scaled. Similarly, one can express a wide class of xt's as a linear combination of e raised to the power j omega t's. And this is the central theme of this part of our syllabus, or this part of the course. Now, towards that objective, we shall first start with functions that are either periodic or are non-zero over a finite interval of time. So, let's begin with a function xt, which is one of the two things. Either it is periodic with a period of t, which means x of t plus t is equal to x of t for all t, or xt is non-zero only over a finite interval of the time axis. So, xt is non-zero only for, say, without any loss of generality, t between 0 and t. Now, in the case of such functions, it is possible to express a wide class of such functions as linear combination of a discrete set of e raised to the power j omega t. Just as if one had a vibrating string we take the string from. In general, under the action of several forces, a vibrating string can have various patterns of displacement along the entire string. But one could think of those patterns as a sum of a set of modes. By modes, we mean displacements according to a sinusoidal pattern, where each sinusoid has a finite integral number of cycles on the string length. What are we saying in effect? We are saying that the sine wave frequencies in terms of which you can express the displacements of the string are all multiples of a fundamental frequency. So there is a minimum frequency which allows only one cycle on that string length, and all other frequencies are multiples of this. So they allow an integral number of cycles, a higher number of integer cycles on the string length. And any displacement on the string, any displacement pattern on the string can be thought of as a linear combination of all these modal displacements. What are we saying in effect? We are saying that we shall consider the following e raised to the power j omega t's. Now please recognize that considering e raised to the power j omega t is equivalent to considering sine. Pair of e raised, we saw in the previous lecture that a pair of e raised to the power j omega t's give you a sine wave. When you have two e raised to the power j omega t's with equal magnitude, exactly opposite starting angle and exactly opposite angular velocity, but the same magnitude of the angular velocity, it produces a sine wave, right? Every sine can be visualized as comprising in it two e raised to the power j omega t's. Now in fact, e raised to the power j omega t's are more general, because they can allow you to have complex valued functions. So instead of working with sine waves, we will work with e raised to the power j omega t, because they allow you complex valued functions even over a restricted interval. Alright? Now the question is, agreed that we can think of a given xt, which is p. See, again here, try and bring this similarity between functions that are periodic and functions that are defined in a finite interval. You might wonder why we are restricting our attention to these two, or is there any relationship between these two classes? Well, notice that if you have a function defined in a finite interval of t, then you don't care what the function is outside that. So one particular function which you might consider for the purpose of analysis is a function which is a periodic extension of this. So if xt is defined on the interval of 0 to t, you could shift xt by all multiples of t and add these shifted versions to the original xt to get a periodic function. Can you see that? So if I take xt and shift it by all multiples of t and add it to the original xt, it gives me a periodic repetition. And in the interval 0 to t of interest, that function is unchanged, right? So if your interest is only in the function in the interval 0 to t, then it doesn't matter if you have periodically extended the function by repetition. And the response of the system to the function, we shall see, will be unaffected by this extension, right? So in that sense, there is an difference between periodic functions and functions that are defined or are of interest only over over a certain interval. So therefore, if you visualize that interval of 0 to t as a string, what he is saying is, consider all those e raised to the power j omega t's which have a finite number of cycles on this interval. So which means consider all omega of the form a multiple of 2 pi divided by t. You see, if the angular frequency is 2 pi by t, it has one cycle over the interval. And any multiple of this, so let us take the kth multiple and we will call that omega k. So what we are saying is, if a function xt is as above, is periodic with period t, then it can be expressed as a linear combination of e raised to the power j omega kt for k belonging to the set of integers. Right? Now, we must emphasize a point here. K are the set of integers, not just a set of positive natural numbers. What it means is you need both positive and negative k. And why do you need both positive and negative k? Because that's right, a combination of a positive and a negative k gives you a sine wave. So if you wish to construct real functions, you will need both positive and negative k. Yeah? And how will the fact that the function is real manifest itself in the coefficients of the linear combination? How will it manifest itself? Yes, yes. That's right. For a given k, so k equal to say plus k naught and k equal to minus k naught, you will have the same magnitude and opposite phase, right? So for the same k naught, I mean, so how would you write this in the language of complex numbers? I mean, suppose the coefficient of k naught is a complex number z. What would be the complex number for minus k naught? Z bar. Is that right? So it would be z bar. So the complex numbers in the linear combination, now please note they will be complex numbers. Why will they be complex numbers? Because the magnitude of the complex number would denote the magnitude of the phasor. And the phase of the complex number would tell you the starting angle of the phasor. And the starting angle of the phasor for corresponding positive and negative k should be equal and opposite, and the magnitude must be the same. So you see, the next question now is, how do we find these coefficients in the linear combination? Now, to that objective, we shall take our thinking of functions or thinking of sequences as vectors even further. Now, if you can think of functions as vectors, then it should be possible to define certain operations between vectors. Of course, addition is no problem, right? So addition, subtraction, scaling is no problem. But we would like to have operations between vectors that we are familiar with. For example, a dot product. Or we'd like to define the notion of magnitude of a vector. So in fact, the idea of a magnitude of a vector can be inferred from the idea of the dot product. Because if you can take the dot product of two vectors, then if I happen to take the dot product of a vector with itself, it gives me the square of the magnitude, right? Similarly, I can define distances between vectors if I can define magnitudes. Because once I can subtract two vectors, then the magnitude square and the magnitude of the difference between two vectors is an indication of the distance between the vectors. So in fact, if I have, so it's a hierarchy. If I can take care of the definition of a dot product for vectors, then I can take care of all the other requirements of the operations between vectors. Now here again, let us take recourse to our understanding of vectors as in the context of 3 dimensions or 2 dimensions. Suppose I have two two-dimensional vectors. Let's say they are A1, x, where here I mean by x cap a unit vector in the x direction, right, plus A2 y cap. And if I have another vector B1 x cap plus B2 y cap, then the dot product between them defined or is obtained by taking a product of the corresponding coordinates and adding up these products. So I would A B1 plus A2 B2. Is that right? Now this argument can be taken further. So for example, suppose you think of each point time as a dimension. Then the dot product of two functions defined on time is, now you see, since time is a continuous parameter, we can no longer take recourse to addition, rather we have to replace it by integration. And then we need to do the following. So if I have two functions, xt and yt, both of them functions on time, then from the dot product between these two functions should look like integral xt yt dt. This is a candidate for the dot product between x and y. Perfectly fine, but there is a problem with this when we start using the dot product to give us other kinds of properties. So for example, suppose we wish to use the dot product to give us the notion of a magnitude of a vector. Then what should we be doing? In fact, this is a notation. Let's denote this by, the vector, the dot product is also called an inner product between vectors. So let's denote this by the inner product of x and y. Here you must think of x and y not as functions but as vectors. So this is an inner product. Now if this is the inner product, inner product of x with x, which is, if we accept this definition, integral x squared t dt, indicative of the magnitude squared of the vector x. Now there is an objection to this definition, because in general if x is complex, x squared is also complex, and this would be a complex valued integral. And that does not serve our purpose at all, because a magnitude cannot be complex. In fact, a magnitude must be non-negative. Not only that, we'd like a magnitude to be strictly positive if the vector is non-zero. So in fact, that's what we want out of a magnitude. We'd like the magnitude to be strictly positive if the vector is non-zero, and in general, we'd like the magnitude to be non-negative. So we need to make a modification to create a non-negative number here. And how can we create a non-negative number here? By taking the magnitude squared instead of the squared. And how will we take magnitude squared? If we allow a complex conjugate on the second argument. So we modify the definition of the dot product just a little bit by conjugating the second argument. Now what happens is, when you take the dot product of x with itself, it doesn't give you x squared t, it gives you mod x squared t dt. They are in good shape, because mod x squared is definitely bound to be non-zero someplace when xt is non-zero. So its integral is definitely going to give you a non-zero value if xt is non-zero. Further, if xt is 0 everywhere, this quantity is strictly 0. So therefore, this indeed does give you the notion of a magnitude vector as we understand it conventionally. So here both the dot product between two functions and the magnitude. I must mention at this point that this is one notion of dot products between functions. And for the sake of this course, we shall really focus only on this version of the dot product. But I thought I should mention at this point that there are several dot products that can be defined on functions. And therefore, there are several different ideas of magnitude that can be induced by them. And they have their own uses. But we shall not, look at other possibilities at the moment. We shall be with this definition of the dot product. Now, in the language of dot products, let us look back. So we saw the expression h omega given by integral h lambda e raised to the power minus j omega lambda d lambda. And of course, this converges. Those h. Now, let's rewrite this. Let's rewrite this as integral ht. I mean, it doesn't matter what call the variable of integration. Let's call it ht e raised to the power j omega t complex conjugate dt. Is that right? We may rewrite. Now this gives us a beautiful interpretation. What are we saying here? What is h? Yeah? Anyone? Is it a unit? Yeah. Is it a unit vector or? Yeah, I mean, see, definitely there's a dot product involved here, right? Dot product between what? Dot product between what? Yeah, dot product between? Yeah? The impulse response, yeah, that's right. That's right. So it's a dot product between the impulse response of the system and one of those basis functions with which we wish to deal, right? We wish to deal with the functions e raised to the power j omega t. And we wish to deal with a collection of functions of this kind. So it's like saying, well, I know what the system does, along a particular direction. Or another way of saying it is, if I have a system in the x, y and z directions I know, then any force acting or any input acting on the system should be resolved into its x, y and z component. And then I look at the action in the x direction, y direction and z direction separately and then combine the actions to get the overall action of the system. Now, how would you resolve a force into its x, y and z directions? By taking a dot product, right? That's exactly what you're doing here. So h of omega is like the component of the impulse response in the direction omega, so to speak, right? Now, if I am dealing with a finite interval of time, 0 to t, then what I have said in effect is that I don't require all the continuous values of omega. I need only discrete values of omega given by multiples of 2 pi by t. In other words, those omega which have an integer number of cycles in the interval t, right? So, how can we carry this dot product to that situation? Well, we will carry it by again making use of the notion of the dot product, also taking into account the fact that, well, right? So, you see, after all, if you have a function xt of interest only in the interval 0 to t, then its component in the direction e raised to the power j omega k t would be xt e raised to the power j omega k t complex conjugate dt integrated, but I will need to put a constant to take care of the fact that this may not be a unit vector. So, when I take a dot product in a, along a particular direction, I need to normalize the vector in that direction. So, I allow for a constant k0 here. Why do I put this constant? Because I need to take care of the fact that this may not quite be a unit vector. Yeah? So, let us, so this in fact this constant may be dependent on omega k, it may be independent of omega k. We will find go along, right? We will find out. And we shall call this quantity Ck. It is the coefficient along the kth direction. So, now you see it is interesting. If you have a finite interval t, then you have discrete points on the omega. See, you can also think of omega as a real axis now. See, omega also takes on real values. Omega can take on any value between minus infinity and plus infinity. It's like a frequency axis. And on this frequency axis, what I'm doing here is to take specific points, omega equal to omega k, for all integers k, right? At the point omega equal to omega k, I'm putting down a number Ck. That's what I'm doing here. Is that right? So, therefore, our claim is that we should be able to say that xt is equal to, xt should be a linear combination of these. So, we should have xt equal to summation on all k going from minus infinity to plus infinity integers. Ck times e raised to the power j 2 pi by t times kt. This is what we want. What I am writing here is a reconstruction. If I know the component Ck in each direction k, then I can reconstruct the vector by multiplying the original, multiplying each component by a vector in that direction. Now again here, as I said, this may not quite be a unit vector, right? So, I need to put a constant there, so I may do is, you see, we are putting a constant on the analysis side. Analysis side means the place where we are obtaining Ck's. We are also trying to put a constant here. Now, what I can do is I can put a constant on one of them to take care of both of these. So, what I will do is I shall not put any constant here. I will put the constant only on the analysis side. So, I will let that constant k0 take care of a constant which is required here and also a constant that is required there. Now, how will I obtain that constant? Well, I should, here you are saying that xt is this and there you are saying that Ck is this. They should be consistent. So, now if I use this expansion of xt and I try to obtain a particular Cl for a particular choice of integer L, I should get the correct value. Is that right? Let us endeavor to do that. Now, let us take the dot product xt times e raised to the power. So, in fact, let me write it here. Now, the dot, so xt e raised to the power minus j 2 pi by t times Lt dt integrated with a constant k0 should give me Cl. This should give me Cl. Is that right? Now I need to have consistency. So what I'll do is I'll substitute for xt here. I'll substitute for xt here. So I'll rewrite this as k0 integral summation on k ck e raised to the power j 2 pi by t times kt into e raised to the power minus j 2 pi by t times Lt dt. Yeah. And it should give me the expression Cl. Right? Now, what I can do is, you see, I can take note of the fact that here this summation on k, ck and all this business does not, I mean, the integral on t acts only on these terms. Now, that integral on t is a finite length integral. So I can bring it into the summation. So let me rewrite this as k0 times summation on k integral. Now in fact ck can also go outside. E raised to the power j, now I shall combine the terms, 2 pi by t k minus L into t dt. Yeah. Now you see, we'll evaluate this. This integral is not difficult to evaluate. But before we do that, let's first get a feel of what we are doing here. Right? What is this integral? And what out of this? What we want out of this is that there's an infinite summation on k, ck and c0 here. Right? Now, only, I mean, the effect should be that k equal to L survives and all other integrals drop to 0. Now, if you look at this not equal to L here, what do we have here? We have a phasor rotating with an angular velocity of 2 pi by t times k minus L. In general, what we have here is an integral of a phasor rotating with an angular velocity of 2 pi by t into k minus L. Now, if k minus L is not equal to 0, this phasor has a non-zero velocity. And what we are doing now, what is the range of the integral here? The range of the integral is t. So it could be, in particular, you could take it from 0 to t. Right? 0 to t. So what are we trying to do? We are trying to find the integral of this phasor on an interval which contains a finite number of cycles, which contains, in fact, k minus L cycles, to be precise. Now, what happens when you integrate over a finite number of cycles? It becomes 0, because it reaches the same point from which it started. So, therefore, integral is going to be 0 except for k equal to L. Yeah? 0 except for k equal to L. Yeah? Now for k equal to L, now in fact we can even, now this was, a geometric visualization of the integral, or this was an intuitive reasoning, but we can also evaluate the integral directly. Let's do that as well for completeness. Integral e raised to the power j 2 pi by t times k minus L t dt is simply e raised to the power j 2 pi by t times k minus L t divided by j 2 pi by t into k minus L. And this is substituted from 0 to t. Yeah, this is substituted from 0 to t. There. So if k is not equal to L, of course here k not equal to L. Yeah. So it's very clear that the phasor acquires the same value at 0 and at t, and both of them are equal to 1. So the integral is 0. In any case, now let's consider the case. So you see, all the terms k is not equal to L drop out from the summation, and the only term that survives is with k equal to L, right? With k equal to L, what is the term? It simply becomes, what is the integral for k equal to L? Well, it's simply integral dt. That's capital T. So what do we have now? Now we have CL, k equal to L, CL K0 times to CL. Yeah? And therefore, K0 is 1 by T. Okay? Now, notice that here we have taken care of the K0 or the only on one side, right? We could have, some people like, some people who like to be very symmetric, like to put on the analysis side and 1 by square root of t on the synthesis side. Synthesis side means the place where you reconstruct. So, actually if you look at it, the quantity t is far easier to deal with than square root of t. So, normally we tend to put this constant on the side of analysis. Analysis is the side where we obtain the coefficient ck from the function. So, we talk about the analysis and the synthesis equation. The analysis equation gives us the ck from the xt. The synthesis equation gives us back xt from the ck, right? And we put the constant only on the analysis side. But in some texts or in some references, they might like to distribute this constant on both the sides, putting 1 by root of t on both. So what do we have? So here we have a Fourier series expansion. So periodic with period or of interest only over an interval of t, 0 to t, can be expanded as a sum of phasors, summation k ck e raised to the power j 2 pi by t times kt, with ck defined by 1 by t. Now notice that this is independent of the constant k, independent of the index of the frequency, right? So it's independent of the frequency. E raised to the power minus j 2 pi by t times kt dt, integrated from 0 to t. There are several important points that one must emphasize here. If you have a function which is periodic or limited in terms of its interest in time, then although the original function is continuous, one can express it in terms of discrete sequence. That's a very interesting point that one must emphasize here. The discrete sequence, I mean, you may think of ck as a sequence in k. Just as you could think of any other sequence x of n, you could think of this as a sequence on k. Because you have in for every integer, right? So what it really means is that this is a transformation that takes you from what was apparent continuous time function to a discrete sequence, the Fourier series representation. It says that a discrete sequence is sufficient to information. Whatever was is also there in the sequence Ck. All right. In fact, in that light or in that language, we could now visualize a system as follows. We could visualize a system as follows. You get a sequence function xt as input, which is either periodic or which periodically I'll say xt periodic, period t. This is put into a system, whatever you wish to call it, we'll give it a name later, which produces the sequence Ck. Call that this denotes a set of integers. So, Ck, k belonging to z. So, here is an example of a system that takes for its input a continuous time signal and produces as its output a discrete sequence. I had mentioned earlier that one can have hybrid systems, and this is an example of such a hybrid system. So, you could think of this operation of calculating the Fourier series as a system operation acting on xt. What does the system operation do? It takes the continuous time signal xt and produces a discrete sequence Ck, which also maintains the complete information. Now, here I would like to bring up the notion of invertibility, which we have not explicitly been talking about all this while. See, this system is invertible. By invertible, I mean I can have another system which goes the other way, which can take in Ck as an input and produce xt as an output. The analysis equation that we wrote down, which gives us the expression for Ck in terms of xt, is a system description for this system. And the synthesis equation that we wrote down will be the description of the inverse system. So, you can have an inverse system here. It can take in Ck as an input. And produce xt. This is synthesis. Right? Now, on one signal, but the aim of carrying out this transformation was to see the effect of a system on xt. So, if I feed xt into a linear shift invariant system, what happens at the output is what I want to answer out of the analysis that I am doing, right? So, in principle, what I should be doing is looking at this kind of a represent, or I should think of a system nature acting on xt, system on this nature acting on the impulse response of the LSI system ht. Something should happen between the outputs of these two systems, and the result of that should give me some insight into what the output of the LSI is, right? Now, in fact, that is not very difficult to see. See, in fact, let's invoke now the property of the LSI system. Let's look at this inverse system. Think of the xt as a set of e raised to the power j omega kTs. Yeah? So let's think of this xt going into an LSI system. So you have xt of this nature, periodic, which can be expressed as summation on k ck e raised to the power j 2 pi by t times kt going into the LSI system. With impulse response ht. And the question is, what is the output? Well, how will I find that out? How can I use the properties of linearity and shift invariance? So first, in fact, forget about linearity and shift. First, let's use the property of linearity. If I consider any one of these functions, so let me first forget summation on k. Consider only this. If I know the output to this, then I can find the output to this by the property of scaling. Then by the property of additivity, I can find the output to this. But I know the output to this. I already know the output to this. If that output is h, that's right, h at 2 pi by t times k multiply e raised to the power j 2 pi by t times k, kt. So I already know the output to this. So in fact, in a short, I can write down the output to the input xt. So now I write, if I put in straight away, if I put in xt into the system, the output is simply going to be the following: summation on k ck h evaluated at omega k, which is 2 pi by t times k, e raised to the power j 2 pi by t kt. A very powerful statement. What we are saying here is that if I have a Fourier series representation of the input, I automatically have a Fourier series representation of the output. And what are the coefficients in the Fourier series? The coefficients are ck times h into 2 pi by t multiplied by k. What are, once again, you think of the function h omega as a continuous function of omega now. So let h omega be thought of as a continuous function in omega. Of course, we agree that it may not converge all the time, but suppose it converges for all omega. Let's take the case now. That means we are dealing with a more restricted class of LSI systems. Those LSI systems where this quantity h omega converges. That class of LSI systems, we have a continuous function h omega of omega, described by ht integrated e raised to the power minus j omega t dt. Now, what are we saying in this equation? We are saying that the kth Fourier series coefficient in the output is equal to the kth Fourier series coefficient in the input multiplied evaluated at omega equal to 2 pi by t times k, the frequency omega k. It's a pointwise operation. It's a very strong statement. The first thing that we are saying here without realizing it is that if I have a function which is periodic with a period of capital T, if xt is periodic with a period t, then the output is also periodic with period t. We are saying that implicitly here. In fact, now what we should do is to prove that independently of this. Let's now prove that if you put into an LSI system an input xt which is periodic with a period of t, the output is also periodic with a period of t. We'll prove that independent of this. Of course, it's a consequence of this, but we'll prove it independent of this. Right? Now that's very easy to see if we write down the input-output relationship. If we put in x lambda, xt, into the system with impulse response ht, the output, of course, is given by the convolution. The convolution is described by the integral. Well, it will be easier for us to write h lambda x t minus lambda d lambda. This is yt. Now suppose xt is periodic with a period of t. So x is equal to plus t for all t. Then consider yt plus t. Consider, by definition, t x t plus capital T minus lambda d lambda. Alright? But x t plus capital T minus lambda is equal to x of t minus lambda because xt is periodic. And therefore, equal to integral h lambda x of t minus lambda d lambda. Which is equal to y of t. So the output yt is also periodic with a period of t. Okay? Only as a consequence, we would express it as a Fourier series, right? And we also had an explicit description for the functions of the Fourier series. With this, then, we conclude this lecture, but with a little remark. We have implicitly assumed that every periodic function with a period of t has a Fourier series expansion. Now, this is as good or as bad a statement as saying that every function that we deal with has a Taylor series expansion. Here with Taylor series or Maclaurin series from our study of functions. So even in the context of Fourier series, there are some functions where a Fourier series may not exist. At this point in time, in this lecture, we'll only be satisfied with the remark that most reasonable functions that we deal with have a Fourier series. But in the next lecture, we shall be a little careful to delineate functions that do not have a Fourier series. And that shall come from a set of conditions called the Dirichlet conditions. With this